Good morning, everyone. Welcome to the snowy Indiana. I hope this cold weather is not going to stop us from learning. Okay, so what we're going to do today is to talk about this law of large number. If you're new to random process, random variable, probability, I guess one of the questions is, what is really randomness, right? What is really randomness? You talk about lots of these PDFs, PMFs, a lot of equations. Ultimately, what is randomness, and why do we want to learn about this randomness? And the moment that I really got clicked is when I learned about this law of large number. I want to tell you at least my experience of learning this, because when you think about random variables, the first moment you got into random variable is that, okay, there's a PDF, there's a PMF, and then you start to talk about the integrals, double integrals, triple integrals, and then you mess up the calculus, and then you sort of just got lost, right? But the whole spirit behind this random variable statistics is all about you have a lot of these, okay? Now, of course, when you go to the math department, they would disagree with me. Okay, that's a beautiful bread measure, whatever. Okay, I don't care. So when you think about the randomness, you're doing this experiment many, many times, right? You always do this experiment many, many times. And the whole concept of statistics is that as you do this experiment, a lot of times, where will it become, okay? And in physics, if you like physics, we all know that measuring individual molecules is extremely, extremely tedious and difficult. So imagine that you have a box, okay, and there are air molecules. They're bouncing back and forth. And so if you want to be very, very precise, you want to talk about the individual molecule movements, measuring the F equals to ma for every molecule. That's insane, okay. So instead, what we usually do is that we look at this entire box. We say, look, what would be the overall direction of the movement of all these molecules? The moment you talk about on average, you're talking about the sample average. You're already leaving this microscopic perspective to a macroscopic perspective. And this is very important because you go out and talk about Twitter, you talk about Facebook, you have lots and lots of connections, many, many data points. You don't want to look at individual person because that really doesn't tell you much of what is going on in the overall global structure right now, right? You want to look at, hey, today, how many people have Twitter? Okay, so this kind of statistics will be useful. And then where does it go? Where does it come from? All these global statistics. So whenever you talk about global statistics, you're already talking about the sample average, okay? And then in statistics, a big branch will be that, okay, what will happen at the limit? This is what the law of large number is going to tell you. And of course, in practice, you will never go to the infinity. You can only say, I have only 30 samples, what will happen? Then you can say, okay, with only 30 samples, how confident am I with respect to my estimate? That goes to the confidence intervals and estimation theory, right? So finite sample behavior, and then ultimately you go to this infinite sample behavior. Okay. So if you want to understand probability statistics, understanding this behavior of the law of large number really helps you to understand what is going on. You really flip the coin many, many times. As the number of times increases, your distribution originally, you're spreading really, really widely. It becomes converging to a delta function. Okay? This behavior of converging to a delta function for that sample average, this number, tells you a lot. Okay, how many samples do you need in order to make sure that you are within certain bound, right? So that is the whole spirit here. Okay, so let me start by reminding you what is this law of large number. We have a sequence of random variables x1, x2 through xn. And then I'm going to form a term called the xm bar, which is the sample average summing from 1 to n of the small xn. And I just take the sum divided by total number of samples. And this n is going to grow. Okay? This big n is going to grow. So the picture that you should really have in mind is that you have an n that is sitting on the x-axis. This is the number of samples you have to construct your new random variable, x bar. Okay? Now, I keep mentioning that each xn is a random variable. Therefore, the sample average, this xn bar, is also a random variable. And by a random variable, I mean that it has its own PDF, it has its own mean, it has its own variance. Okay, so this is a random variable. This random variable is different from the population mean. The population mean is just a constant, which is the expected value of the individual. And you can show that by law of large number that this xn bar is going to converge to this mu. Again, we need to be very precise about what do I mean by this converging. One thing you can check is that if you take the expected value of this x bar, it will return you the population mean. Okay, because this is a random variable, so you can talk about the expectation. So going back to this graph, you have all these n. Here, if you have a very small n, let's say 10, then you have a sample average that is constructed using 10 samples. It has a distribution. The distribution could be something like this. I don't know what it is, but it has a distribution. You can have a sample average that's constructed from 100 samples. It has its own distribution. I don't know what that distribution is, but I'm guaranteed that it will become narrower. It has to be, because I'm using more samples, and so it has to concentrate more in the mean. So now, if I go to 10,000 samples, then I don't know what the distribution is, but I'm pretty sure it will be very concentrated. Okay? So every n, big N, you have a random variable. And these random variables, they are going to have their own PDFs. Then they will converge to something. They converge to something. Okay, so this is the notion of this convergence. Convergence, when you think about the convergence of random variables, is always the PDF or the value. The value, okay? So how should we describe it? The way to describe it is that you're going to look at the deviation. This is a random variable. I'm going to subtract from the population mean. This is a deterministic quantity. This is a random variable. I'm going to set a absolute value to measure the deviation so that I don't have to worry about which side I am at. I'm going to compare it with a epsilon, which is my tolerance level. And if this is true, this is an event, right? This is an event that is either true or false. I want this event, it is called a bad event. I want this bad event to be as small as possible as my n becomes big. Okay, so here I am measuring the deviation with respect to my epsilon. It is a bad event. The probability of this bad event has to be small as my n goes to infinity. So this has to converge to 0 as n goes to infinity. This is what we call the law of large number. And now if you're still wondering, why can't we just say xn bar going to mu? This is not allowed because here you have a random variable which has its own PDF, PMF, blah, 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 everything, okay? It's not a number. It's not a number. And so you cannot say a sequence of random variables converging to a number. Yeah, we can define it that way. That is what we call the almost sure convergence, okay? We can define it that way. But here, we're not even there. We're not even there. We're always saying is that, okay, so here you have a sequence of random variables. They all have their PDFs. They all have the PDFs. And then now the only way of convergence that we have learned so far in calculus is that you have a sequence of real numbers, right? So you can say the limit of a sequence of real numbers, they're approaching to some number. So you can say, okay, given the epsilon, there's a delta, and then you can make that kind of statement. Here it doesn't work. Okay? Now, why is this statement work? Well, here I have an event. An event is either true or false, yes or no. I can measure the probability of having that event. And the probability of that event is just a number between 0 and 1. And this is a number, it is a number that is indexed by this capital N. And so if I use a small n, then I would expect that there will be really high probability of getting some bad events because I only have a few samples to construct my sample average. So very likely that I will have bad samples. They are falling outside this tolerance level. As I am making this n bigger and bigger, I think that this probability of getting a bad event will become smaller and smaller. So you will have a convergence. This convergence is about the convergence of a sequence of real numbers. Real numbers in the range of 0 and 1. Those are the real numbers for the probability. So that kind of convergence is well defined. This is called the law of large number. It has a name. It's called the weak law of large number. Okay, it's called a weak law. And of course, there's a strong law. Strong law is a lot harder to prove. Now, what I want to do is to talk about how we prove this weak law of large number. The proof is interesting. It is not the most powerful proof. Okay, and powerful means that, as I'm going to say, the probability inequality, the bounds that we're going to give is not very tight. Okay, however, it still can give you the conclusion. Strong law requires a lot more things to do. Okay, so this is 6.5 law of large number. Before I go there, let me just make sure that we have covered all the important messages from the slides. So the sample average, sample variance, we can do the calculation. We can show that it is converging to 0. This is an experiment we showed the last time, right? Python code, this is great. And this is what I mean by the weak law of large number. So this is a formal statement. There's a criteria that your second moment is bounded. There's a picture illustrating what is going on. Okay, and there are examples. If you have a sequence of Gaussian, you're going to converge to a new Gaussian because you can show that the variance getting to 0. So this is something that we have seen last time. So this is great. Okay, so just to make sure that everything is covered. So this is the numerical experiment. So we have seen the last time. And you can see that this delta here is just the probability for my Gaussian. So it is this bad event probability. I have a notation called a delta n. And you can see that as n becomes bigger and bigger, you can actually go to 10 to the power minus 23. So it is really converging. So it's a numerical experiment that you can find it from the textbook. Okay, so let's talk about the proof. Okay, let's talk about the proof. For the proof, we need two sets of inequalities. And that goes to a section that we haven't talked about yet. It's called the Markov and Chebyshev inequality. So this is 6.4. Okay, so what are these two inequalities? Let me write it here. We want to look at the, let me write the Markov inequality. And then there's a Chebyshev inequality. Okay, what we want? Well, we want to have a way to measure this, right? So this is what we want. Now, when you look at this kind of statement, probability of some kind of event, and you want to show that it is going to 0, right? You want to show that this is going to 0. What would be the good way? Well, the good way is that you want to bound it by something. Okay? You want to bound it by something. You upper bound it by something. If this is less than or equal to something, and hopefully this is less than n, over n, okay, reverse engineer. And now if you set n goes to infinity, what will happen to the right-hand side? You have got to 0, okay? So if you, this is what we want, okay? My desire, okay? This is Christmas gift, okay? This is what I want, okay? This is what I want. So now let's go back and see what can we show. Well, Chebyshev inequality says that if you have any random variable, okay, x minus mu bigger than epsilon, it is going to be less than or equals to sigma square divided by epsilon square. Okay, sigma square divided by epsilon square. Now, it is not exactly what we want because there isn't any n. But anyway, this is close enough. At least the left-hand side is similar to this. So if I can show this result, maybe there is a hope that I can show this result. Okay. Now, how do I get to this Chebyshev inequality? Well, I look at this event inside. I have this absolute value, and I don't want to deal with the absolute value. So what should I do here? So let's do something else. How about I just talk about this? That's even simpler, right? And it turns out that this is going to be less than or equals to expected value of x divided by epsilon. Okay, so these are the two inequalities. Okay, so now what we should do is to connect the dots. I'm going to first show you the Markov inequality to convince you that this is true. And then I'm going to use the Markov inequality to show the Chebyshev inequality. From the Chebyshev inequality, I can show you the final result. And the beauty is that this sequence of argument doesn't really depend on the specific distribution of x. It can be Bernoulli, it can be binomial, it can be any distribution as long as they have a finite second moment. That's very good. Okay, so let's get started with this Markov inequality. How should we prove it? That doesn't seem interesting. How can we prove the statement? Let me make sure that I have the right thing here. Okay. All right. Of course, I don't expect you to know how to prove it. Maybe except one or two students in this class who you have learned it before. At least I don't know how to prove it when I first read it. So what can we do here? Well, let's consider this. This is not trivial. So you have a random variable, okay, x. And then you have an epsilon. And let's calculate this product. Epsilon times probability of this. And you may ask, why are you considering this? There's no reason here. All right, so let's just go through it, and then you can see why we want to start with this. Okay, so you have this epsilon times the probability. Now, what is the probability? The probability is what fx dx integration. The integration should have two limits, lower limit and upper limit. And since I'm measuring x is bigger than epsilon, what should be the limit? 0 to infinity. Yeah. Epsilon to infinity. Let's do it. Epsilon to infinity. Okay. Okay, let epsilon to infinity. Okay, great. Now, here's a trick. The trick is very important. It's a very difficult trick. The difficult trick is to move the epsilon inside. Okay. Wow, this is very important. How difficult is it? Well, it looks trivial, but it's actually quite non-trivial. Quite non-trivial. Okay, not the mathematical argument, but how can you think about the step of moving this epsilon inside? Yes? Yeah, it's not hard at all, right? Mathematically, there's no difficulty. But how can you think about moving this epsilon inside? And consequently, the next step. The next step is to recognize that you're integrating with respect to x. And your x is integrated from epsilon to infinity. Therefore, all your x has to be bigger than or equals to your epsilon. Right? Because you're integrating your x is between epsilon and infinity. You're doing this integration. Okay? And so, I can replace it by an x here. This is really non-trivial. Okay, why? Well, because you are integrating with respect to your x, and your x is during your integral, you're only integrating your x from epsilon to infinity. And therefore, you can replace your epsilon by your x. That's non-trivial. And because this is so non-trivial, you will never do this step in the beginning. Because you will never think about, okay, I'm going to use this. All right? So then what? Okay. Then I am also going to need an assumption, a little assumption here, which I will comment on later. The assumption is my x is positive. Now, that's a negative case, which I'm going to deal with later on. So the Markov inequality is that if x is bigger than 0, then this holds. Okay, so let's go back to here. If x is bigger than 0, then your x is positive, your PDF is positive. You integrate this positive times positive, it has to be positive. And so it has to be bigger than or equals to this, or less than or equals to this. You change the epsilon to 0. Why? Because they're positive, and so you're integrating a narrower region. Now you integrate a wider region, and of course, this bigger integral has to give you a higher number. Can anyone really think from here to here? I cannot. I admit that when I was a student, I was not able to go from here to here. That's non-trivial, very non-trivial. Okay, so now once you're here, then what it is? Oh, that's just expectation. Why? Because your x is between 0 and infinity. Your x is bigger than 0. And so you're integrating the entire sample range, entire sample space, x times fx, that's your expectation. Oh, go back here. Oh, we're done. We're proved this result. Question?
Yeah.
You got it? Okay, let me pause for a second. This is not trivial, okay? It takes a while to click it. Any questions so far? Okay. All right, so every step logically makes sense, but then if I don't tell you the proof, it's very difficult to come up with this proof. But now you know the proof. So, so this is the Markov inequality. And if you want to read the slides, I think this is the full statement. Let x be a non-negative random variable. Okay, this is page 3. Then for any epsilon bigger than 0, we have this probability less than or equals to the expected value of x divided by epsilon. Whether you have this straight inequality or greater than or equals to, it doesn't matter, because usually we are dealing with a continuous random variable, so the equal case doesn't really matter. So that's the statement. The proof, if you want a typed proof, this is the typed proof. Okay, it's the same thing. Now the picture is interesting, although I don't really think it is useful. It's an interesting perspective, but it's not that useful. Why it is true? Because you can draw the CDF, and it turns out that the if you integrate the CDF, this pink portion, it is equal to the expected value. That is a result that we have never proved. Okay, so you need to first know this proof. And then you can crop out this area, the yellow region, and you can see that this is the epsilon times your probability. Then you can see that, okay, this is going to be less than my expected value. I'm not sure how useful is this picture, but I still draw it just to make it complete. Okay. All right, so now, how good is this Markov inequality? Let's look at this example. You have a uniform random variable. X is between 0 and 4. Verify the Markov inequality for x bigger than 2, 3, 4, and so on. Okay. So what do I want to show? Well, the Markov inequality says that probability of x bigger than or equals to epsilon has to be less than or equals to expected value of x divided by epsilon. Okay, so under what condition can I declare that my Markov inequality is valid? Well, look at the random variable. I put in an epsilon. I calculate the expected value. I check whether the left-hand side is less than the right-hand side. If this is true, I say that the inequality is valid. So given this example, let's just see. So you have this uniform random variable, x from 0 to 4, okay? So the expected value of x is 2. That's very easy, right? Uniform from 0 to 4, so it will be midpoint. So I have this checked. Then I have all these epsilons. The epsilons 2, 3, and 4. So what do I need to check? I just need to check x is bigger than 2. Would it be less than or equals to expected value of x divided by 2? Is it true? Okay, if I can come up with a case that is not true, then it's either my mistake or there's a problem with the statement. Okay, so let's just verify that. So x bigger than or equals to 2, it is the, for this uniform random variable. Now what is this? What is this? Uniform, okay, from 0 to 4. The probability that my random variable is bigger than 2, this is 1/2. So this is 1/2. Is it less than or equals to expected value, which is 2, divided by 2, which is 1. Oh, true. Okay. For 3.25, and then the right-hand side is 0.67. Oh, that's valid. This is 0, this is 0.5. Oh, this is valid. Okay, so at least I think I have convinced you that for these 3 special cases, the Markov inequality is valid. All right. So is it a very powerful inequality? No. It's very loose. It's super loose. Okay. By loose, I mean that the actual probability you want and then the bound that you can predict, the bound is very, very, very high. It's so high that it doesn't tell you anything. So it's just like, oh, I have a probability, and then it is upper bounded by 1. Now, the 1 is a valid upper bound, of course, but you are not going to get worse than 1 because all the probability has to be less than or equals to 1. So even though when you have an upper bound, doesn't mean that you have a useful upper bound. So just keep in mind that, okay? Now, the Markov inequality may not be that useful, but then it can help us prove the second inequality, which can then tell us about the law of large number. The second inequality is called the Chebyshev inequality. And this inequality has a lot of similarity compared to the previous one, with only one exception that you have this absolute value. Well, that's a deviation from the mean, but that's easy to take care of. Okay, so how should we do it? Well, it's not too bad. How about we start with the Chebyshev inequality? X minus mu bigger than epsilon. Well, let's put it equal to. Okay, so you start with this inequality, and let's do the following. I don't like absolute value, but I do like squares. Okay, so let's just put the squares. Okay, when you put a square, does it look like this one, the Markov? It doesn't look like, the Markov doesn't have a square. Okay, and there's no square for the epsilon. That's easy. That's very easy. Do you like apple and orange? You like that. I know you like that because you have been in this class for a while. Do you like this? Apple bigger than banana. Banana is easier to draw. Do you like that? You like that? Okay, see that? See now? It's the same thing. And so what will it become? It will become expected value of your apple divided by your banana. That's it. right? And so let's put in the number. So you have this thing here. It will be less than or equals to the expected value of your x minus mu squared divided by epsilon squared. And what is the expected value of x minus mu squared? There's a name. There's a name. Variance. Okay. Thank you. So this is variance of x divided by epsilon squared, which is also sigma squared divided by epsilon squared. Oh, proved. Okay, statement proved. So you can see that while the Markov inequality is not that useful, okay, but it can be used to prove something very useful. Chebyshev is one of those. Okay, so now you have the Chebyshev inequality. We are still not done yet. We're still not done yet. How do we move from the Chebyshev inequality, all right, from here, to the law of large number? Well, we only need one more step, which is to replace my x by xm bar. And then let's do it. Let's just do it. Okay, so you have probability of xm bar minus mu bigger than or equals to epsilon. This is less than or equals to. Now you have to put the variance of xm bar of epsilon squared. Do we have questions here? Do you guys have questions? Okay. All right, good. So, okay, so this is what? This is actually just the Chebyshev inequality. What I'm doing here is that I'm replacing my x by x bar. Okay, I'm replacing my x by x bar. So this is true. This inequality is true by Chebyshev. Okay, this is true by Chebyshev inequality. And so what I want is that I want to show the final result, which is the probability of something less than or equals to something divided by n. So let's see if I can get to this formula. And all I need to do is to look at the this right-hand side. So the variance of my xm bar is, it does look like someone has a question. Okay, good. Let me pause for a second. Ladies and gentlemen, if you have a question, you can ask. We welcome your question a lot, okay? All right, so this is variance. Now, the variance of xm bar is what? Well, it is the variance of 1 over n, n going from 1 to capital N and xn. Okay, and so what is this variance? Well, the variance, when you apply to the n, you get the n squared. You have the summation n going from 1 to capital N, and then you have variance of individual xn's. All right, because they're all independent, and so the covariance term, they are not there. And so you can do this. And now, what is this? What is the variance? The variance is sigma squared, and then you have n of these sigma squares. And so you have 1 over n squared of sigma squared plus dot 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 plus sigma squared. And so you have n times sigma squared. And now you have n times sigma squared divided by n squared. So what do we have left? You have sigma squared divided by n. Okay, so you have sigma squared divided by n. Now what is sigma squared divided by n? Let's just plug in the formula. You will have probability of xm bar minus mu bigger than or equals to epsilon. This is less than sigma squared divided by epsilon squared, and then there's an n. Oh, good news. We have found this new territory. It's like when Columbus found Cuba. Okay, we found the new territory, the new world. Okay, so now you see this thing. So sigma squared divided by epsilon squared, that's an n. And finally, let's just put the limit of n going to infinity of this thing here. Then it will be less than equals to the limit of n going to infinity of sigma squared divided by epsilon squared of n. And what is this? This is my favorite number. It's called 0. And so the result is proved. Very beautiful result. Very, very beautiful result. It is so powerful that the weak law of large number is true for any distribution as long as they have a second moment. Okay, finite second moment. The reason that you need a finite second moment is that you're putting a variance here. You assume that the variance is finite. If your variance is going to explode, then of course it doesn't work. Now, as for how big your n has to be, that is a question that you need to ask. So what do we have? We say that this probability of xn minus mu bigger than equals to epsilon is less than sigma squared divided by epsilon squared. There's an n here. Now that tells you a lot of things. Number one, if I want my sample variance to be very, very close to my true population mean, the probability will be upper bounded by this. So if I have a known sigma square, I have a known epsilon square, I need to tell you how big the n is. Let me give you an example. So let's say you have a random variable. Your sigma is 1. Okay? Your sigma is 1. And then your epsilon is 0.1. And then you want your deviation, right? You want your deviation probability of your sample mean. I don't care what distribution you have. I don't even know what the mean is. Okay? I don't care. I just want to make sure that you are not too far away from the mean. The deviation is 0.1, so this is 0.1. I'm just asking this probability. And then I know from the Chebyshev inequality, it is sigma square, so it is 1 divided by 0.1 square times n. Okay? This is the upper bound. So I want this to be small. Then you got to tell me how small you want, how comfortable. Okay? If you're a really conservative person, you want this probability to be extremely, extremely small. Right? So this is what you want. So let's say you want this number to be, give me a number so that can make you feel comfortable. It has to be small, right? Because there's a bad event. You want it to be very confident. How about 99% or 99.9%? Okay, 99.9%. So this is 0.001. You want this number to be 0.001. Okay. So what? Well, you want this 0.1 squared times n to be equal to 0.001. Well, this has to be less than, right? This number has to be less than 0.001 in order for this to be less than 0.001. For the logic, right? I'm setting an upper bound on this upper bound because I don't want to make sure that this probability is less than my confidence level, which is 0.1%. And so I know that upper bound just bound a little bit more. So we do the calculation, and let's see what do we have. Well, you move the n to here. You move the 0.001 down there. So you will have n bigger than 0.1 squared times 0.001. This is how many zeros? 1, 2, 3, 4. Okay? You need to have 4 zeros. So basically, it says that n has to be bigger than 1, 2, 3, 4. You need that many n's to guarantee that this is less than 0.001. You need that many n. Okay? To make sure that the probability of getting this bad event is small. Now, at this point, you may say, 10,000 samples, it's not a big deal on computers today, okay? But the problem is that it is just overly conservative. In fact, when you do experiments, you can show that you may just need 30 or 40 n to get this probability to be less than or equals to 0.01. You may just need 30 or 40 samples. Is there something wrong with the Chebyshev inequality? Nothing wrong. It is still a valid bound. But a valid bound doesn't mean that it is a very good bound. Right? It is still valid. Well, if I have 10,000 samples, of course, I can guarantee that your probability is less than this number. Of course. I'm just so conservative. I have so many numbers. But do you need this many numbers? No. Okay? And so there is a big branch of work called the large sample theory or the large deviation theory. What they study is that how do we analyze this event using a lot tighter bounds? Then people come up with all these beautiful bounds called the Hoeffding inequality, Bernstein inequality, all these crazy inequalities. Okay, there's a Chernoff bound and things like that. So all these things they all come out from this need to get a much more tighter upper bound. So to just comment on one thing, at least to motivate you to think about this Markov inequality and also moment generating function, I want to tell you one thing that is not going to be needed for you. I think for 90% of you, you will need it for your lifetime, but I will still tell you. Okay. So what would be the possible way to get a very, very powerful bound? I'm going to tell you a principle in case you need it later on in your career. Okay. So I want to look at this event, x bigger than epsilon. Okay, this is less than equals to expected value of x divided by epsilon. This is Markov. Okay, a very useless bound. All right. So here is the very powerful thing that again I cannot think of. So you take e to the power x, e to the power epsilon. You can do that. Okay? You can do that. And then if you do this, it will just become x. And then e to the power epsilon. You can just do that. Now why? Because apple and orange. You just map it. Okay? So you can do that. And there's one more thing, is that I'm going to assign a constant, a positive constant called s. I'm going to assign this constant s. Why on this earth you want to do this? Anyway, this is a transformation. It is a monotonically increasing transformation that if I applied it here, it doesn't change my inequality. I just change the right-hand side. Okay? So that's the step one of the principle. Now, this thing is exactly equal to that. So if I can find this thing here, I am finding upper bound for the original thing. So I'm good. Now, what is this? Expected value of e to the power sx divided by e s epsilon. Can anyone tell me what is the numerator? There's a name. Moment generating function, mx of s. Okay, moment generating function divided by e to the power s epsilon. And then I want to write it in this way. I want to write it in terms of exponential. Okay, so now you have s epsilon, so minus s epsilon in the denominator, so I have minus s epsilon. And I also want to have the mx, so I put a log of mx of s. All right, so now I have this. Now, that means what? That means your probability of x bigger than or equals to epsilon is less than that. It is a function of your s. Okay, it's a function of s on the right-hand side. Okay, very, very puzzling. Why do I have this? Now, look at this inequality. This inequality is true for all s. For all s. Any s I can choose from, including one very special s. One very, very special S. This S can make this thing the smallest. There is one S, well, there are many, many, many S. Some S can make this quantity big, some S can make this quantity small. There is one S that can make this quantity the smallest. Okay, there is one S that can make this quantity the smallest. I don't know what it is, but I know it exists. Okay, I don't know what it is, I know it exists. Okay, so what is this? Well, this is of course going to be less than technically it's called an infimum, but I'm going to write the minimum. Minimum, you find an S that can make this whole. Okay, just find the S that can make this guy minimized. You can find this S. I don't know what it is, but I know it exists. And the minimization can go inside the exponential, because exponential is monotonically increasing. It doesn't change my minimizer. So this is the same as exp of the mean of S of this minus S epsilon plus the log of mx of S. Okay? It has a name. It's called the Legendre transform, a French name, very beautiful name. Okay? Legendre transform of the moment generating function, the log moment generating function. It's a big branch of topic in probability. Okay? You want to do this. All right, so now you do all these crazy things. Basically, it means that you want to minimize this function. Now, if I give you the Gaussian distribution, you can actually plug in. You can actually plug into this formula. Okay, log of your moment generating for a Gaussian function is just a quadratic. Ladies and gentlemen, you can do that by yourself. Put your Gaussian inside. You can minimize it. It's a quadratic function. Take the derivative, set it to 0. You can minimize it. Okay, you can do that. Once you do that, you can plug this in again. You just put your minimizer. Call it S star. That is the minimizer for this equation. Put it back here. Okay, that will give you a very, very tight upper bound. That will give you a very, very tight upper bound. And this is called the Chernoff bound. Okay, the Chernoff bound. This entire, now I'm not talking about a specific distribution. I'm just saying that this logical argument from the Markov to all these Legendre transforms and stuff like that 99% of you will not use it, okay, except one. It's called a Chernoff bound. It's called a Chernoff bound. Okay. If you do machine learning theory, you do all these provably approximately correct framework, you need to use this thing called a Chernoff bound. Okay, it comes from here. It comes from all the way from the Markov inequality, the useless inequality, to this very, very powerful inequality. And you can show, for example, if you plug in the Gaussian distribution, you put a quadratic, you can minimize it, plug it in. You can show that it is virtually almost exact. Very, very tight. Very, very tight bound. So tight that if you do the experiment, the experiment would be n, right? N. And then you measure the probability of xn bar minus mu bigger than epsilon. You can do this, right? And now you can show that the Chebyshev inequality goes like this. The Chernoff inequality goes like this. Okay. Now you may ask, then which one is correct? The true one is something like this. It is in that level of magnitude, the approximation. Is that good? Okay. So you can go home and try the Gaussian case. The Gaussian case is very easy to prove because you know this log of moment generating function of S, you know the moment generating function of a Gaussian, right? And so the log would just be mu times S divided by mu times S plus sigma square S squared divided by 2. Okay, so you can plug it in and then you have another term, quadratic equation, take derivative, set to 0, you can actually find the optimum S. Plug it in, you get the formula. that formula is very, very tight if you do the experiment. Okay, so I stop at this point, and then when we come back on Friday, I will talk about the central limit theorem.